Okay, chemists, today we're going to review types of reactions and so let's remember what we learned. So our first type of reaction that we learned was a simple synthesis, meaning that two elements react to form a compound. So aluminum and chlorine react together. Now remember, aluminum's always a +3 and chloride is a -1. So they're going to come together in the same way every single time, and they're going to form AlCl3. Now you say to yourself, that doesn't make any sense because how can I have 3 chlorines on one side and 2 on the other side? That's where balancing comes in. And remember, we're going to double the odd when we balance to make our lives easier. This is a synthesis reaction. Now let's check out what the driving forces for this particular reaction would be. Aluminum starts out with an oxidation state of 0 because remember, elements who are standing by themselves have an oxidation state of 0. I'm going to put the states of matter here so we can check for some other driving forces. Over here, aluminum has a +3 and chloride has a -1. So the driving force for this particular reaction is redox. Remember our acronym GRUs. Formation of a gas is what G stands for. We did not form a gas. Redox, we already figured out that it is a redox. Formation of water, we did not form water. There's no water on the product side. And the other one is formation of a solid. Remember, that has to be a solid that comes from two aqueous solutions, a special kind of solid called a precipitate. Our next type of reaction is when we had one reactant. When we have one reactant that falls apart, it's a dead giveaway that it is a decomposition reaction. This is decomp. So we can always identify synthesis because it has one product. And decomposition has one reactant. Now let's figure out what the driving forces for this reaction are. Well, you've got the chlorate ion here, ClO3 -1. That tells us that oxygen is -2 here. Chloride has to be +5. Potassium's always +1 because remember we have 3 oxygens that are -2. So I have 6 minuses back here. So I have to have 6 pluses up here. So that's how I know that chlorine's a +5. Now we go to the other side. Potassium didn't change, so it's not part of the redox situation. Oxygen is in its elemental state, so it is a 0. Remember, that's a dead giveaway for a redox reaction when you have substance that's in a compound on one side and it is standing alone on the other side. So this is redox. We have only a solid on the reactant side, but we have a solid and a gas on the product side, so it's also formation of a gas. Last step, we're going to balance it. Remember, we have odd oxygens here, so we'll double that, like such. Remember that we had all sorts of practice with balancing, so if you're still struggling with balancing, go back to those videos and go back to those assignments and practice those again. Our next one is a single displacement reaction. So a single displacement reaction has somebody standing by himself and somebody in a compound. Like such. So remember, this is where you would look at the activity series in your reference packet. In the activity series, you're going to compare iron and silver. Remember, everybody wants to be in a compound. So in order for iron to be able to kick silver out of the compound, he has to be more active. So you find iron and you find silver, and you see that iron is more reactive, so iron can kick him out. If it wasn't more reactive, you would put no reaction. Let's go ahead and balance this. We're going to have to put a 2 here and a 2 here. Single displacement reactions are always redox because there's always somebody standing by himself on one side and alone on the other side. So they're always redox. We did not form a gas. We did not form water. And we did not form a solid, because remember, a solid is a special kind of solid that is a precipitate that comes from 2 aqueous solutions. So let's do that one next. So when we're doing a double displacement reaction, they're going to switch partners. So you have 2 aqueous solutions. And they're going to be put into a container together. And then when you add them together, seemingly out of nowhere, you're going to get a solid. So you're going to look on so barium's not going to be with nitrate anymore. We're going to look on our solubility table in our reference packet. So barium's going to be with carbonate. And if you find barium on the left-hand side and run your finger over the carbonate ion, you'll see the letter I. That means it's insoluble. That means it's going to form a solid. And then sodium's not going to be with carbonate anymore. It'll be with nitrate. Remember, they're going to switch partners, but you can't put 2 positives together and you can't put 2 negatives together. All nitrates are soluble, and all sodium or all alkali metal are soluble also. So this is a double displacement reaction, a special double displacement reaction, which is called a precipitation reaction. So you could also call this a precipitation. And when you have a precipitation, remember, double displacements are never redox. When you have a precipitation reaction, formation of a solid is always the driving force. You could have another type of double displacement reaction where you take a strong acid and a strong base and add them together. So I'm going to take a strong base and add it to a strong acid. These are both aqueous. When you put them together, you're going to get a salt, which is sodium sulfate, and water, which is a liquid. So this is a double displacement reaction also, but this is a acid-base neutralization reaction. And the driving force is the same for all neutralization reactions. It's formation of water. Balance that. So our last type of reaction is combustion. This particular hydrocarbon is called butane. You might have recognized that name from talking about butane lighters. Whenever you combust a hydrocarbon, the products are always the same. It's going to be carbon dioxide and water. Water is usually in a gaseous form because there's so much energy given off by combustion reactions. Now this is going to be a situation, if I put a 5 here to balance the hydrogens, I'm going to recognize that I'm going to get an odd number of oxygens. So I'm going to double that right away. Instead of putting a 5, I'm going to put a 10, which means that I'd have to put a 2 here, and that gives me 8 here. That's going to help me balance it without running into a problem where I've got an odd number of oxygens that I can't balance with the even O2. Now I've got 8 times 2, 16, plus 10 for 26, 13. So let's check. Remember, combustion reactions are always redox because oxygen's by itself on one side. Carbon and oxygen are the ones that are involved in the redox reaction. So this is a combustion reaction. And my products are water. Let's check how many. We've got 2 plus 13 or 15 moles of gas here, and then 8 plus 10 for 18 moles of gas here. So one of our driving forces is formation of a gas, redox, and formation of water. You can't form a solid with any other type of reaction besides double displacement. This was a quick rundown of what we learned in the equations or chemical equations